Hello and welcome to section 15.5 on divergence and curl. So in the last section we defined the two-dimensional divergence and curl. So here we're going to extend those ideas to 3 dimensions. And so to start, I'm going to first introduce some terminology. Now we've been working with multivariable functions and vector fields in this chapter. And so to highlight the fact that these things interact in much the same way as ordinary scalars and vectors, that you see in vector algebra, we're going to refer to multivariable functions as scalar fields. Okay, so now what's a scalar field exactly? Well, as I just said, it's just a multivariable function. So its input here is just going to be a point either in R2 or in R3, and the output is a real number. So in other words, the output is a scalar. So here are 2 such scalar fields. Okay, now we distinguish these from vector fields that we introduced at the beginning of this chapter. Now, vector fields, remember, are just functions whose input are points in either R2 or R3, and the outputs are, well, two-dimensional vectors in the case of a two-dimensional vector field, or three-dimensional vectors, right, in the case of a three-dimensional vector field. All right, so since these fields are functions, right, these things are not just static objects as in vector algebra. Okay, in addition to all the ordinary vector operations like vector addition and subtraction, scalar multiplication, dot product, cross product, right, all that good stuff, we now can perform operations on these fields that involve differentiation. Okay, and so to begin with that, we're going to introduce what's known as the Dell operator. So this upside down triangle capital Del, okay, is the same notation that we use when we define the gradient. Okay, now del on its own, you can see is written as a vector. And notice these components, these partial derivative symbols. Well, there are no functions here, right, that are being differentiated. So you might wonder exactly how it is you should go about thinking about this thing. Well, you want to think about it in much the same way you think about ddx in Calc 1. So this is usually introduced as notation that just says take the derivative. Okay, now you can think about this as a function in its own right. Okay, so now the input is a differentiable function. So you feed this thing a function f, and then it outputs the function's derivative. Okay, much the same here for this del operator. These partial derivative symbols you can think of as awaiting a function to differentiate. Okay, now one of the main benefits of introducing this operator is that the 3 main operations in all of vector calculus, so namely the gradient, the divergence, and the curl, can be very nicely expressed in terms of this operator. So let's go ahead now and walk through each of these operations. So start here with the gradient. Okay, and we know that if I want to compute the gradient of a function f, okay, I just form the vector whose I component is the x derivative of the function, the j component is the y derivative, and the k component is the z derivative. Okay, now I can think about this in a slightly modified way in terms of thinking about scalar fields and vector fields. Okay, so here I'm thinking about taking this scalar field f and applying scalar multiplication to this vector del. Okay, now of course this is not ordinary multiplication, right? When so f distributes to the I component, we're really taking the x derivative of f, and likewise for these other 2 components. Okay, so you can think about the input here is the scalar field f, and the output now is this vector field that we call the gradient. All right, now next up we have what's known as the divergence of a vector field capital F. And here, this can be defined in terms of the Dell operator as a dot product. So we're going to take the Dell vector and dot it with the vector field capital F, and I'll label its components as P, Q, and R. So again, when we go ahead and take the dot product, this is not ordinary multiplication. You want to think about del x here as being applied to the function p. So I'm going to get the x derivative of p there for that first sort of new type of product, right? And then I'm going to get del y of q. So in other words, just the y derivative there of q plus, and then the z derivative of r. Okay, so here I'm thinking of the input as a vector field, capital F, and the output here, right, is not a vector. It's a scalar field, okay? And next up we have the curl, which is taking the cross product of a vector field, capital F, and this Dell operator. Okay, so this definitely probably looks a little strange at first glance. Okay, so I'm going to take the cross product in just the same way I would take the cross product of two ordinary vectors. Okay, so here in the second row of this determinant, I have those partial derivative symbols, and then at the bottom I have the components of the vector f. Okay, and then when I go and perform this determinant, okay, so let's look at the I component first, right? So I cross out the first column, first row, and I'm looking at this little 2 by 2 determinant. But again, when I multiply, again, in quotes here, del y with r, you're really taking the y derivative of r. And then you're going to subtract from that the z derivative of q. And then remember there's that negative in front of the j component. And then I take this 2 by 2 determinant where I delete out the second column in the first row. So I'm going to take the x derivative of r minus the z derivative of p. Okay. And then lastly, for the k component, you delete out row 1 and column 3, and you're taking now the x derivative of q minus the y derivative of p. Okay, so notice here the input is a vector field, capital F, and the output is this thing, which is also a vector field. Okay, all right, now I did include what's known as the Laplacian of a scalar field, which produces another scalar field. I'm not going to go or highlight that right now, but we will see the Laplacian come up from time to time, as it does play a pretty important role in vector calculus amongst lots of other things. Okay, so that's going to do it here. In the next video, we'll go ahead and actually compute a few of these quantities, and we'll just go from there. All right, thanks so much.